Week 5, Wednesday. A couple of things. A few people have done that revision quiz which pops up on the home page for the course when you go there. Quite interesting, some of the misconceptions that's revealed. It'd be good if a lot of people could do that revision quiz just so we got an idea of what people aren't quite understanding. So there's a couple of questions that have been done really badly. I don't know whether it's just the people who did the quiz or whether that's a general problem that exists in the course. So if everyone can have a go at that, then we can talk about the quiz on Monday and clear up those misconceptions. If you're one of those people, fix up your email. Every time Andrew posts a notice and emails it to the class, I get bounced emails from these accounts. And given that I'm getting bounced emails, I can't email you to tell you to fix your email. So that's telling you to fix it. If you're not a CSE student, there's still time to escape from 1511 to 1911. Friday is your last chance. All right, let's get on with some content. So, bit of revision. Char data type allows you to represent characters. Characters are basically the ASCII character set whose ASCII codes go from 0 to 127, and they represent upper and lowercase Roman letters, digits and punctuation characters, plus a few non-printable things. Although you could argue new line is printable, but you can't see anything when you've got new line. So you can define a character variable by saying char and give it a name. You can call it anything you like. Could have called it X, could have called it whatever. You can read it in, if you want to use scanf, using the %C formatting string. And of course, remember that scanf is trying to modify the value of the variable. So you have to pass in its address using ampersand, which we talked about last time. An alternative way is to do something that looks a little bit more like a function. You invoke the function, it gives you back a result, and you assign that to the variable. Similarly, you can print out a single character using %C as the format, or you can use putchar. Getchar and putchar and scanf and printf for that matter are all defined in standard IO.H, so as soon as you hash include that, you can use all of those functions. For dealing with characters or dealing with char values, there's also quite a useful library that has a whole bunch of functions for classifying characters and also I think for doing conversions. So you can check whether a particular character is an uppercase letter, or whether it's an alphabetic thing, upper or lowercase letter, whether it's a space character, whether it's punctuation, and so on. All right, so last time we looked at cat.c, which was a program that simply read its input and wrote it to output using getchar and putchar. Hopefully that's reasonably straightforward, although I did want to do a variation on that. So, hey, oh, that's what I'm in. Let's open cat.c and play with it a bit. Play with the cat. Alright, so here we've got ch equals getchar, well ch not equal end of file, putchar, so get the first character, if it's not end of file, print it out, get the next character, and so on until you find end of file. This program technically has an error, because end of file, in theory, is not a character value. And so, in theory, you can't compare a value of type char to EOF. It happens to work on the CSE machines, but on some machines that won't work. Often what we do is we define the character variable to instead be an int. And then that certainly makes this kind of test legitimate. Because if you think about it, EOF is a value that has to represent something that's not a character at all. So it can't possibly be a char value. So it's a value outside the range of character values. If you declare ch to be an int, then ch can contain values that are outside the range of char values. And one such value is EOF. Right, but since it works on CSV machines and it kind of looks a bit more obvious, I'll leave it as a char. The other thing about this program that you won't typically see in C programs, written by experienced C programmers, is, once again, a big driving force for experienced C programmers is laziness and try to write as little code as possible. Here you can see that we've got ch equals getChar appearing twice. Wouldn't it be good if we didn't have to type it twice? And we can by exploiting the fact that assignment returns a value. There's a question in the quiz that illustrates that, but very often you're going to see something like this in real C programs. We try to keep them a little bit simple here, so as to not confuse you. Now I'll try to confuse you by doing that. Formatting's a bit ugly. Okay, so what this does, it evaluates this expression, which involves making a call to getChar, getting the value back from getChar, assigning it to the variable ch, and the result of that expression is the value that was assigned to ch. Okay? So the value of this whole thing is whatever value getChar returns. In other words, it's the next character in the input. So I can take the value of this sub-expression and compare it to EOF, and I'm done. So you can see that I've saved a line of typing, or a line of code. Always a good idea. And now the fact that the main loop only has one statement in means we can also employ my naughty that Andrew doesn't like, not putting braces around the single statement that comprises the body of the loop. So you can reduce the program to that much, and if you're really desperate to get rid of lines of code, you can do that as well. Okay? But using assignment as part of an expression is quite a common thing to do in C programs, so get used to it. You'll see it. I mean, the reason we're showing you these kind of things is that as soon as you pick up a book like Kernighan and Ritchie, or pretty much any C book, you're going to see stuff like this, rather than the slightly more obvious versions that we write in lectures. So it's worth showing you this every so often, just to prove that it works. I think I always have to do that, don't I? Let's see, so my makefile probably should... One nice thing about makefiles understand what needs to be recompiled. So all of my other programs in this directory that are mentioned by the makefile were already compiled. Cat wasn't, or in fact, cat was compiled, but I just modified cat.c, so make understands, oh, cat.c is newer than the binary cat, so I need to recompile cat.c to make a new cat based on that. So cat and redirecting inputs. We can copy input to output. So the input's coming from a file using redirection, and the output is going to the screen. If I was to do something like this, I'd be slightly annoyed because that would wipe out cat.c. So the first thing the shell does is says, oh, this command wants to write to that file, so I'll zero that file out. And then tries to read the file, which is zeroed out, and you end up with an empty cat.c, which I won't demonstrate because I want to keep it. Of course, if you don't redirect input, then it will read from the keyboard, blah, 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 blah. And notice that the input from the keyboard is line buffered. So it doesn't put char anything until I've typed a whole line of text and hit return. And then it reads the whole line and prints out each character that it sees. Okay, so that's that's a function of the way standard in works when it's connected to the keyboard. And of course remember that to finish input on Unix it's Control D, and that'll just stop. Right, any questions on cat.c? Read character by character from standard input, print each character to standard output. But you know, the other thing that I could have done, I could have said, and that would produce exactly the same result, I hope. Let's see. Once again, make just recompiles cat, and let's see that same thing. Yep.
Why do you use the make file for that?
Because I'm too lazy to type DCC cat.c.
What actually is in the make file?
Huh?
What actually is in the make file?
Oh, alright, I showed you that last time, but I'll show you again. It's actually got quite a bit bigger because I've got makefile entries for all of the programs in this directory, and as you can see, there's quite a few programs in the directory. Alright, so let's open the makefile. So Andrew probably should give you makefiles for all of your labs because it makes it easier. Any Linux machine is going to have make, so knowing how to write makefiles is useful. Right, what I've got in this makefile, I've said what C compiler do I want to use? DCC. So that's simply setting, telling make use DCC to do your compilation. If I didn't have that line, it would use GCC by default. And then I've got a line that tells me what are all the binary files that this makefile is going to build. And because they were too many to fit on a single line, I had to break them over multiple lines, and I have to tell make, this isn't really the end of a line, so you put a backslash and then the new line, and make says, all right, I'll continue reading stuff on the next line. So having these 4 lines here was like having a gigantic line without any of the backslashes in it. Okay, so that's just an annoying thing. All right. So in a makefile, the first entry in the makefile is the thing that will be built when you type make without an argument. And the thing that's going to be built is everything, and basically it's going to build all of the programs that are mentioned up here. So that's what that line is setting up for. So I can just type make and it will rebuild whatever files need to be recompiled based on what .c files I've made changes to. Alright, so how do I make the file add2a? That requires me to have add2a.o and johnslib.o, so my little library which has get number in, for example. You may notice there's no rule here. I think the very first time I mentioned makefiles, I said what you would typically have here is something like so being explicit about how you actually remake add2a from these two .o files. Okay. Make is pretty smart and it understands how to recompile C programs. So it knows if I just say add2a comes from these two things, then it actually produces that command all by itself. So I don't need that line. So that, once again, being a lazy C programmer, that saves me a bit of typing. So you can see all of these programs I've basically just mentioned. Here's I think the sum program we looked at last time. It needs the arrays library, which is a few little functions on arrays that I wrote last time. It uses John's lib because that's got get number in it. And it takes these 3 .o files, puts them together and produces an executable file called sum. Yep.
And is John's lib already defined?
Yep. And John's lib.o is where it comes from, it's defined down here. Okay, so I have to say, how do I make John's lib.o? I make it from johnslip.c and make knows which C command to use to do that. So all this stuff, well, let me see. All right, here I've been a little bit slack, but we'll have to have a look at this in a minute. You don't actually need, unless your program has multiple .o files involved, you can probably just write something like this, say that strings 1 executable comes from strings1.c, so the command that make is going to produce will be something like dcc minus o strings 1. So it doesn't explicitly mention a .o file anyway, but during the compilation process the .o file will be created, and maybe it will be removed at the end, so you don't see it once you've generated the executable. Anyway, so that's what's happening there. Alright, so that's the make file. So the make file's smart, it understands if I make changes to cat.c, let's put that back to be put char. And I save it. Make understands that the current version of cat.c, let's can actually look at that. The current version of cat.c was made at 11.24. The current version of the cat executable was made at 11.19. Therefore, cat.c is more recent than cat. Therefore, cat is out of date with respect to cat.c. Therefore, I need to recompile cat.c in order to make cat. So that's the reasoning that make uses when it's recompiling. So if I type make, and I can even say make cat if I really want to be explicit about it, and it will recompile cat.c and produce cat.o and then use cat.o to make cat. Now you can see here I've only got one .o file, so I don't even need to mention cat.o in fact. And it still would have worked. Alright, anyway, that's just a convenience. Having a make file makes your life a lot easier when you're editing, recompiling, recompiling. It just makes life a whole lot simpler. Alright, so that was cat, read from input, write to output. So the whole point of that was we were talking about characters, and then I wrote a little program that would read character by character, count the number of characters we read, count the number of lines we read, and print out those values at the end. Counted lines simply by checking for new line characters, and as soon as it saw a new line character, it incremented the line counter. Alright, the next character-based thing I wanted to look at is a program that will tell me about characters. So I've already got a binary code, so I'll run it, and because it produces a lot of output, I'm going to type it through the program less, which pages gives me one page of output at a time. Right, so what this program does, it runs through all the possible values for a character starting from 0, 1, 2, 3, 4 up to 127, and for each character, each of those values, it shows me what the code is. So characters are binary values that represent ASCII codes. And as I said before, I think ASCII codes represent Roman letters, digits and punctuation characters, plus a few non-printing characters like these ones. So you can see that all of the low ASCII codes correspond to non-printing characters. If I keep going, we're not getting many non-printing characters. In fact, we won't get any till here. Now, what it does for the rest of the time, it tries to classify each character that it sees. Okay? So it sees a character whose ASCII code is 32. That corresponds to the character space, and because of the way I wrote the program, we'll have a look in a minute, it doesn't know what kind of character that is. So it just says, dunno. ASCII code 33 corresponds to the single character exclamation mark, which is a punctuation character. etc. Once we get down to ASCII code 48, and these are decimal values, by the way, that corresponds to the digit 0, which is different to the integer value 0. Okay, so the digit 0 has value 48, the integer value 0 has value 0. In any case, it knows that this particular character is a digit. And if we keep going, 2, 3, 4, blah, 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 and you can see one interesting thing is that the digit characters happen to occur in a contiguous sequence. So 0, then 1, then 2, then 3, then 4. That has some useful properties when you're trying to convert digits into numbers. More punctuation, then we get some uppercase characters. We get the whole uppercase alphabet, a few more punctuation characters, then we get the lowercase alphabet, then we get some more punctuation characters up to ASCII code 126, which is the tilde character. Right, so that's the whole thing. You can see it's telling me end. All right, what does the program that produces that look like? Right, one thing to notice straight up, uses this library I mentioned in the notes, ctype.h, which contains all these useful functions for classifying characters. I've got a single char variable whose name is ASCII. Oh, what am I doing here? I'm assigning an integer value to a char variable. C is quite happy to almost interchangeably assign numbers, integer values and char values. So I could write ASCII equals 0, or I think I could write, if you really want to, because it's a character, I think this special escape character here represents a character whose ASCII code is 0. Okay, so I could write it like that, but C doesn't really care if you write a number or if you write a character. It does care if you write a number that's larger than 127, because then you'll get an invalid character value. Or what C might do, just use the bottom 7 bits of the integer and give you some random type character. Alright, so let's have a look at the rest of it. So initialize ASCII to 0. While we haven't reached the end of the ASCII values, print out the value of the char as a decimal number. Okay? So, as I said, ASCII values, the integer ASCII values and char values are pretty much interchangeable in C programs. So if I've got ASCII code 32 and I ask to print it as a decimal number, it'll print 32. If I ask to print it as a character, it'll print the space character. If I've got ASCII value 48 and I ask to print it as %D, it'll print 48. If I ask to print it as %C, it'll print the digit 0. So you've got this single chunk of data which can be interpreted in a number of ways. And that's something a lot of programming languages won't let you do. C is a little bit slack about treating data values. So you can take a chunk of data and treat it one way, or you can treat it as a totally different way if you like. Sometimes that can lead to a bit of confusion. But in the case of ASCII codes and characters, it works out quite nicely. Now, you should never write ASCII integer ASCII codes in your program. If you want to put a character into your program, and here I'm just violating that rule, put it in single quotes. So if you want to assign the digit character 0 to a char variable, write CH is assigned quotes 0. Don't write CH is assigned 48. No one will understand what you're doing. Alright, so the C-type library provides a whole bunch of functions. I can check whether a particular character value is a printable character. And if it's not, then I can write out the word non-printing. If it is a printable character, then I'll show what it looks like as a character inside single quotes, and then I'll classify it and I'll write out the classification. Hey, what did I do there? Oh, well, that's pretty bad. Oh no, that's right. I thought I deleted something, but I hadn't. And that's very annoying. Right, so these quotes that I'm putting here, they're literal quotes inside the printf formatting string. I could leave them off and the ASCII character would come out just as a single character, but I put them in deliberately so you can see the extent of the character. And also, if the character is an invisible character like a space, you can actually see there's a pair of quotes with a single space in between, so you know that it's the space character, which we saw here. Okay, if I didn't have those quotes, you'd just see nothing and it would look like it hadn't printed anything in it. Okay, so that's just to make sure that's visible. So print out the ASCII value as a character inside single quotes and then classify it. So if is upper tells me whether the ASCII character corresponds to an uppercase letter, A to Z, and if it is, it'll print out uppercase. Is lower, checks for a lowercase character. Is digit, checks for 0 to 9. Is punct, checks for punctuation characters, and anything else that says, I don't know. There are some other classifiers that we could use, and one possibility is checking for a space, which is why it said the space character was dunno, because I hadn't bothered checking for a space. So let's add that checking. See how that changes things. Oh, actually, so here we've got classic multi-way conditional. Make one test. If that fails, make the next test. If that fails, make the next test. If that fails, if all of these tests fail and it doesn't fit under any one of those categories, then we print out dunno. And then, of course, inside this while loop, we go to the next ASCII value. So ASCII was a char type. C is quite happy to say treat that as a number and add 1 to it. And then if you want to interpret that number as a new character value, that's fine as well. Right, so let's recompile that one. And I think a few of the non-printing ones earlier on will come out as spaces as well. No, they're not. Oh, that's a bit strange. Alright, so now I can see that the space character, rather than being counted as dunno, it recognises it as a space. Now some characters fall under several categories, and in particular some of those early characters, ASCII code 10, ASCII code 12 and ASCII code 8 are also space characters, but they're not showing up as space here because they're also non-printing characters, and so they get picked up by that test there. Okay, so they're not printing, but they're also space. So one particular letter can fall under multiple categories, and in fact there's a bunch of extra categorization functions that you can use. There's isLnum, which tests for an alphabetic character or a number. Isalpha, upper or lowercase letter, and so on and so on. How do you find what all these functions are? Well, you can try asking about one of them, and it will tell you about all the others. So the Unix programmer's manual is your friend, contains a lot of useful information. Just to see what I type then, man is lower, give me the manual entry for the is lower function, and it happens to, in this case, give me all the other functions like is lower, all the other functions that come in that library. Other things to notice, see here it just says it's an int. I've been treating it as a char, like I said, int char. C doesn't care that much. Oh, let me see. Oh yes, one other thing I wanted to show you. The fact that I've written a char here has some interesting side effects. And here, that EOF thing that I mentioned before doesn't cause a problem, but defining it as a char here and then messing up the bounds of the range of possible ASCII values does cause a problem. So, if I happen to make that 128, then I'll show you what happens, and then ask you, or think, once you see what happens, think about why that's happening. Okay? So it kind of makes sense. I said there are 128 ASCII values numbered from 0 to 127. If I've got this test here, in theory that loop is going to stop when ASCII has the value 128. It'll start at 0, 1, 2, 3, 4, 5, keep adding 1, and eventually we'll reach 128. Oh, did I save that? No, I didn't. The C compiler is telling me something anyway. It's telling me that 128 doesn't make sense because 128 is not a valid ASCII value. The valid ASCII values are 0 to 127. So there's a clue that something's going to screw up, but let's see what happens when we try to do this. Alright, so far, still alright, still alright. Still alright, going through the lowercase letters, 123, 124, 127. Alright, it recognises 127 as a non-printing character. But as soon as you go to 128, it suddenly thinks it's a negative number. Okay. Why is that? Because the char data type is actually a signed value. So the first bit in any signed value, and this applies to int as well, the first bit in the signed value kind of gets used as a signed bit. So if that bit's set to 0, you're talking about a positive number. If that bit's set to 1, you're talking about a negative number. Okay, so as soon as that top bit gets set to 1, then we think we're dealing with a negative value, and a negative value 128 is still less than 127. Okay, so it's going to keep going and add 1, add 1, add 1, add 1. So effectively we've had overflow on the set of integer values, and then we'll wrap around and we'll start again, and we'll keep going, and then we'll go back to 128, and it just goes forever. Right? So effectively that's, if you like, character overflow. So you don't want to use the test less than 128. So that's why I used 127. The character 127 isn't printable, so it's not particularly interesting anyway. So I'm happy to stop at 126, which is the tilde. Right, so that's a little thing to be careful about with chars, and that's kind of related to the reason why EOF doesn't always work. It doesn't work on every architecture. It happens to work on the CSE machines, but it won't work everywhere. I think it works on the Mac. It works okay on the Mac as well, but not everywhere. Alright, so that's using the ctype.h library. Alright, well you can go so far with individual characters, but eventually you want to put them together in strings. And so let's take a look at strings. So essentially strings are just arrays of characters, but they always contain a null character as the very last character in the string. It doesn't have to be the last character in the array, but you'll have an array, it'll have A, B, C, D, \0, that's the string A, B, C, D, if you want to write that double quotes. So the \0 character is always used to mark the end of the string. If you want to define a string variable, you can define it as an array of a particular size. How big, how long is a piece of string, how long is a string, it depends. Depends on your application. If you know that you're dealing with people's names, say having size 60 is probably reasonable. There aren't many names longer than that. If you're dealing with lines of text coming from a file, from a book, say, maybe 200 characters is a reasonable maximum string length, but we always add 1 to make sure we've got space to store the null character. If you fill up the array and you don't put a null character, then you're going to see some slightly weird behaviour. You'll see all of the characters in the string and then some garbage until you eventually find a 0 byte which looks like a null character, and then C will think you've reached the end of the string. So, as I said, you choose your maximum string length depending on your application. Technically, this array is not really a string, it's a buffer that can hold a string value. Okay, so a string buffer. How do we use string buffers? Well, input and output, fget will read in a line of input. If the line happens to be longer than max strillen, then fget will stop at that point so you don't overflow the buffer. If the input line is shorter than max strillen, let's say it's 10 characters, the 10 characters from the line will be stored in the array, or in the string buffer str, and then a new line will be added at the end, and then a null character. So that's what you'll get from doing an fget. And if you want to print out the contents of a string buffer, fputs will print it to standard output. And in the case of fgets and fputs, you have to be explicit about where the string is coming from or where it's going to. Okay, so standard in and standard out we haven't had to use explicitly, but in fact printf, like this, is really just shorthand. Once again you can see that switching between two worlds. So printf is actually just shorthand for that. So print to a named output string. Now of course, the C library functions have this beautiful inconsistency that this function puts the string as the first argument, and this function puts the output stream as the last argument, which is slightly annoying because there are plenty of functions that I can never remember what order the arguments go in, but you know, man is your friend. Well, tell me about printf, and all right, man can sometimes be your friend. Here it's not being super your friend, This printf that it's telling me about is actually a command that I can use on the command line. I hope that works. Okay, so that's a printf that I can run from the command line if I'm really excited about that. If I want to see the library function printf, I have to say, tell me about the printf that's in section 3 of the manual, because I happen to know that section 3 of the manual tells me about library functions. Okay. So section 1 of the manual tells you about command line things, ls, make, all of those kind of commands, gedit. Section 2 is system calls, section 3 is libraries. And so if I type man3 printf, it'll tell me that not only do I have printf and fprintf, I have sprintf, snprintf, and all these variations of printf. Most of the time we simply use that one. Occasionally, if we want to write to a specific output stream, we could use fprintf. And here are the signatures. Printf is a slightly weird function because most functions have a fixed number of parameters. If you think factorial, it's got one input. A function to add two numbers has two parameters, two number parameters. Printf has as many parameters as you need, which is the reason for that ... there. It always, the first argument to printf is always a character string, which gives the format of what you want to print. If that format contains %d or %c or whatever, then you need to have some additional parameters here. Okay. So it is a slightly weird function, but anyway, man3, any library function, and that applies to all those C-type ones as well, which you may have noticed there's a 3 up here when we look at that. Alright, so why was I talking about that? Oh yes, fputs, you have to name where you want the output to go. You can't do fputs to standard input because it's not a stream that you can write on. Okay, it's an input stream. So C understands the difference between an input stream. It expects you to read from an input stream using things like scanf or fgets, and for an output stream it expects you, the only things you're allowed to do are to write on that stream. Alright, so that's input and output of strings. And there's also a library that has a whole bunch of functions on strings. It's called string.h. Annoyingly, there's another library called strings.h, which doesn't have all of these functions in. So you've got to remember string.h is the function with all of these. So strlen will take a string as an argument and tell you how long the string is. strcopy takes two string buffers as argument and copies the contents of the second string buffer to the first string buffer. And I just happen to have a diagram to show this. So here's the string buffer. Can hold strings of up to length 9, because we always have to allow space for the end of string character. And here it's got a string. I forgot to type the I, and then couldn't be bothered going back and adding it. So it's got this string starts with the character A, then has the space character, then the character S, T, R, N, G, and that character there terminates. Now, that string doesn't happen to fill the string buffer. What's in these elements in the string buffer? Who knows? We don't care, right? They're effectively uninitialized variables, like when you declare int I, and if you straight away printf int I, you just get garbage. So it doesn't matter that these are garbage values. If you're using all the string functions from string.h, they'll recognize that the string ends at that point there, and they'll be happy. Right, here's another string buffer. Happens to be 1 byte longer, So it means you could store strings up to length 10, and it currently happens to hold the string hello and whatever. We don't care. So if I was to say f puts from B to standard out, it would print the string hello on standard output. Okay, so the string copy function takes a string from the second argument, and here it's trying to sort of mimic the order that you write things when you're doing assignment. So here's one way that you might think to make string buffer B contain the same value as string buffer A. That's not how you do that, okay? If you say B is assigned A, then you're likely to get a compiler error, but even if you didn't, all you'd be doing is making B be the same array as A, the same object. You're not copying the contents of A into B, you're making B and A. The names B and A refer to the same object. So you can't copy strings like that, you have to use string copy. So if we did string copy from A into B, then that's what we end up with. So the character A will be copied from the first element of A into the first element of B, that space will be copied across, and so on and so on, and we'll end up with the two string buffers containing the same string value. If I wanted to check whether that was indeed the case, that they did contain the same string value, once again, we can't do that. Doesn't work. Now, if you think back to what I said just before about A is assigned B, what this is actually checking is, do the names A and B refer to the same string buffer? Not two different string buffers with the same contents, but actually, are they the same string buffer? And clearly they're not. A is different to B, so that test would fail even if the two buffers contained exactly the same string, which they do here. All right? So if you want to compare strings, there's a function for doing that called string compare. So you should be using that. So string copy is a way of copying strings around, or if you like, assigning strings, even though it's not assignment. So there's string copy. String cat will append a string onto an existing string in a string buffer. And string compare is the function for comparing two string values. String copy and string cat aren't careful about the size of the buffer that you're copying into. And so let's go back to our diagram. If B happened to be length 4 and all it had, or length 5, HELL \0, and that was the entire array. So let's mess up my beautiful diagram. Let's take this part of the array away, pretend it's not actually there, and let's say that B looked like that. If I try to do this string copy, then I'm going to end up with a mess. So let's drag that away as well. Back. Sure, I'll copy A, S, T, R, and then I'll keep copying into whatever comes after the string buffer B, which could be anything. It could be one of your other variables. there might be some part of the memory that you're not allowed to copy into. So you might end up throwing a memory error. So these functions aren't particularly careful about how much they copy, and they certainly don't understand how big the string buffer is that they're copying into. So you need to be careful about that. Possibly, there's a couple of comparable functions. There's a function called strncopy, which will copy the first n characters from a buffer. So if you know how large the output buffer is, you can set the n value to be the size of that buffer, and so it won't overflow it. But if I did something like this, copying these 8 characters into here, then the characters would end up in the memory. They'd end up in the memory after the end of that string buffer, and as I said, they could write on top of anything, and you don't know what's going to get screwed up when you do that. Alright, so what else do I want to say about them? Oh yeah, alright, so let's take a look. Oh no, we won't. We'll have a break and then we'll take a look at some programs to manipulate strings.